In this video, we're going to get into calorimetry in chemical reactions. Okay, so essentially what this is measuring energy changes in the lab. That is what we call calorimetry. And when we try to measure energy changes, we need to make two assumptions. So we're making the assumption that energy is being conserved, which just means that it's not lost to the environment when we're taking these measurements of heat transfer. And number two, heat flows from hot to cold until thermal equilibrium is reached. So what thermal equilibrium means is that when you have heat transferring from some hot object to a cold object and eventually they reach the same temperature, that's thermal equilibrium. Okay, now these assumptions are derived from the first two laws of thermodynamics. So the first law of thermodynamics is just the conservation of energy, which means energy can change forms, but it is neither created nor destroyed. And the second law just states that heat is going to flow from a hot object to a cold object. Now, for calorimetry type calculations, we're always going to be coming back to this heat lost is equal to heat gain. So, for example, if we have some type of combustion reaction where heat is being given off by the reaction and it takes place in something called a calorimeter, which is a special device to help us measure energy transfers or heat transfers. So, if we have a combustion reaction happen within a calorimeter, we can measure the heat lost by that combustion reaction by measuring the temperature change that's caused by the heat gained of the water or the calorimeter. Okay, so for example, when you place ice in a glass of liquid, energy is going to flow into the ice because it's colder. So again, we're coming back to that heat flows from a hot object to a cold object. Now the energy is going to break the bonds holding the ice crystal's structure in place. Now we can measure the amount of heat entering the ice indirectly. All we need to do is find the heat lost by the liquid and then assume the heat lost by the liquid is going to be equal to the heat gained by ice. Now, in chemistry, water is cheap and has a very high heat capacity, so it actually works quite great in calorimetry labs. Its high heat capacity allows us to keep water as a liquid, and then calculating energy gained or lost by water is basically a very simple kinetic energy calculation. So in the lab, to help these assumptions, we use a calorimeter. For phase changes, we often use a styrofoam calorimeter like the one below here. Okay, so effectively, different calorimeters are better for different types of reactions or applications. Okay, so styrofoam calorimeter, that's one of the more common ones in a high school chemistry lab. And the nice thing about it is that this calorimeter is insulated, so it minimizes heat movement with the outer environment, so it doesn't affect your results. As well, because it is assumed to be perfectly insulated, the calorimeter does not need to be included in the calculations. Okay, so this is going to be good for solutions, aqueous solutions, and reactions. Okay, so when we have a styrofoam cup, the formula that we're going to be using is this. So moles times molar enthalpy is equal to mass times specific heat capacity times the change in temperature. Now, to calculate the heat of fusion or the heat of reactions using a calorimeter, the following data is needed. So the mass or moles of the substance that's undergoing either a phase change or a chemical reaction. So that's going to be moles, and that's this moles in the formula. We also need the mass of water in the inner container, the change in temperature, the specific heat of water, and if the calorimeter is metal, then we'll also be needing the mass and temperature change of that calorimeter, as well as the specific heat capacity of the metal calorimeter if we have one. Okay. So with this part here, this is your MC delta T. Okay. So if you have a mass of water, you need your water's specific heat capacity, and then you need the change in temperature of said sample of water. Okay. All right, now this does say that you need the specific heat of the can substance, so that's just talking about the calorimeter, and it says usually it's aluminum or copper, but not always. Always be sure to read the question and see what's given to you in the question. Another type of calorimeter is going to be a metal can calorimeter. So usually these calorimeters are made of copper or aluminum, so they're good conductors. And these calorimeters are great for finding heat of a flame or combustion reactions. So you need to include MC delta T of the can as well as water. So what that means is you're going to have two kinetic energy terms. Okay, you're going to have the kinetic energy of the water as well as the metal can. So with these calculations, sometimes students do get confused about what information they should put on what side. And for me, the easiest way to differentiate what goes in the potential energy part, which is the moles times the molar enthalpy part, the information that goes there is gonna be the information related to the substance that undergoes a chemical reaction. Whereas the kinetic energy part of your equation, that is going to be related to the substances that do not undergo a chemical reaction. They just undergo a temperature change. So that's why when we're looking at the kinetic energy of the calorimeter, there's two parts to the calorimeter. There's the water part and then the metal can part. Okay. So I'm just going to write out what I said prior. There's two kinetic energy terms. Okay, and as a reminder, kinetic energy is equal to mass times specific heat times by the change in temperature. Now, with the last one, that's bomb calorimeters, they sound a lot more exciting than they actually are. However, they are not on the diploma, so you don't need to worry about it. All right, so if you want, you can read through that, but otherwise I'm going to be moving on. All right, so why calorimetry works. So it's based off of the first two laws of thermodynamics, the first one being the law of conservation of energy, which, as I stated previously, it just means that energy is neither created nor destroyed, it just changes from one form to another. So the energy released from a chemical reaction in a calorimeter changes the temperature of the calorimeter and the water surrounding it. And we're going to pay attention to heat lost by a system is going to be equal to the heat gained by the surroundings. Okay, and we're going to keep on coming back to that heat lost by system is equal to heat lost by or heat gained by surroundings. With the second law of thermodynamics, it just states that thermal energy is spontaneously transferred from an object at a higher temperature to an object at a lower temperature until they reach the same temperature or thermal equilibrium. Okay, and again, that's what I was talking about earlier when I said heat flows from a hot object to a cold object until they reach the same temperature. All right, so there's going to be two formulas that you need to get familiar with. There's the formula for exothermic reactions, and then the formula for endothermic reaction. Now, they only differ in where the negative is placed here. And the reason why the negative is placed on the potential energy part, or the part that deals with the chemical reaction, is because in exothermic reactions, heat is being given off by the reaction, so it's being lost. And in order to make both sides equal, since this is going to be a negative value, we need to times it by a negative in order to make both the left and right side equal. But the main point that you need to know is this formula here. Okay. So negative moles times molar enthalpy is equal to MC delta T. For endothermic reactions, the negative is on the side that talks about the surroundings. And that's because for endothermic reactions, the surroundings lose heat in order to get the reaction started. So that's why the negative is there, is just to make left side equal to right side. Okay, but this is the main point that you need to know. So you must calculate heat on both sides in the same units, and usually we end up calculating them in kilojoules, but not always. So in our first example, we have 5 grams of butane is burned with excess oxygen from a butane-powered camp stove to heat 10 liters of water from 19.5 degrees to 30 degrees Celsius. In these conditions, what is the molar enthalpy change for the combustion of butane? So what this question is asking for, molar enthalpy of combustion of butane. So that we have no clue. Now with everything else, I just want to draw a little picture. So we got our container that we don't know what substance it's made out of, but that's okay. And then we have our flames from our butane camp stove there. All right, so writing out our list of givens. For our mass of water is a little bit of a trick before we actually get into it, but you got to remember that 1 milliliter of water is equal to 1 gram of water. So then 1 liter of water is equal to 1 kilogram of water. So for our water, we have 10 liters. Now we could say, okay, well then that's 10 kilograms. How many grams are there in a kilogram? Well, there's 1,000 grams in a kilogram. If we have 10 kilograms, we have 10,000 grams of water. Now the question also talks about the temperature change of water. So remember, to find temperature change, you just go final minus initial. So for this, the initial is going to be that 19.5 degrees and the final will be 30. How I'm figuring that out is the temperature that's mentioned first is going to be your initial. So 30 minus 19.5 is going to give us 10.5 degrees Celsius. All right. So last but not least, we have the mass of butane given to us, which is 5 grams. Okay, so I'm going to take a pause from my list of givens and talk about the formula that we're going to be using. So we're going back to this idea of heat lost is equal to heat gain. So because this is a combustion reaction, I'm going to be using this to start out my formula. Okay, so remember that the left-hand side of this equation is talking about potential energy, whereas the right-hand side is talking about kinetic energy. Now, since it's an exothermic reaction and heat is being lost from this reaction, the negative is going to go on the left-hand side. Okay, now at this point, what I'm going to do is just flesh out the left-hand side of this equation. So just as a reminder, potential energy is equal to the change in enthalpy, which is equal to the moles times molar enthalpy of reaction. So what I'm doing is I'm going to expand this to this part of the equation. And since we know it's a combustion reaction, I'm going to put C for combustion, and all of this is for butane. Now for the kinetic energy part of this formula, remember kinetic energy only talks about the substance that is undergoing a temperature change, but not a chemical reaction. The potential energy part of this formula talks about the substance undergoing the chemical reaction and not just a temperature change. Okay, so for the kinetic energy side, as a reminder, kinetic energy is equal to mass times specific heat times the change in temperature. And the substance that just went under a temperature change was water. So this belongs to water. So the question asks us to find the molar enthalpy of combustion of butane, so we want to find this. So how we're going to isolate it is by dividing by moles or negative moles. So the molar enthalpy of combustion of butane is equal to mass times specific heat times the change in temperature. So everything that's blue relates to water. Anything that's pink relates to butane. Divided by negative n. So this is the equation that we are using here. So the mass of our water, that's 10,000 grams. The specific heat capacity of water, we can go to page 3 of our data booklet, and it's right here. So it's 4.19 joules per gram degree Celsius. And then the change in temperature was at 10.5 degrees Celsius. Okay, now the problem here is that we don't have a value for N. So before we carry on, we need to figure out what moles of butane are, because remember, anything that's pink relates to butane. So let's go back and look at butane. And remember that moles is equal to the mass divided by molar mass. So if I want to figure out the moles of butane, I'm going to go the 5 grams of butane divided by the molar mass of butane, which is 58.14 grams per mole. So if I put that into my calculator, that's going to give me 0.0859, goes on forever. So grams canceled out, so we're left with moles. So as a reminder, yep, I am putting ... That just means that the number goes on forever, but in subsequent calculations, I am going to use the entire raw number that I got in my calculator here. All right, so now that I have my moles of butane, I can keep on keeping on over here. So what I can do is go 10,000 times by 4.19 times by 10.5. Close the brackets. The reason why I'm putting brackets around this whole thing is just to represent that all of these are in the numerator. Divide by negative, second function, and then answer. And there we have it. So we got negative 511,500. Oh, hang on. That's not that. Sorry, that would be negative 5,115,738. 0.6. And now with units, let's take a look at what's happening. So grams is on the top and the bottom there, so they cancel out. Degrees Celsius cancels out. Nothing else does. So we are talking about this in joules per mole. Okay, so now we need to look at our question, and it looks like all the numbers given to us were in 3 significant digits, so our answer needs to be in 3 significant digits. So 1, 2, 3. There's my cutoff line. So because the cutoff line comes before the decimal point, I'm going to need scientific notation. So we're going to move the decimal so that there's only 1 digit to the left of the decimal that is not 0. So 1, 2, 3, 4, 5, 6. So negative 5.12 times 10 to the power of 6 joules per mole. So this value right here is the molar enthalpy of combustion for butane specifically, not any other substance. All right, so with these types of questions, if you're looking for a general game plan with how to tackle them, here's what I would suggest. Okay, so step one, label or organize any information that you're given. So do your list of givens, and if it helps you, you can draw pictures. Step two, if your reaction is exothermic, then you're going to be using this formula. If your reaction is endothermic, then you're going to be using this formula. Oh, forgot the negative there. Step three, use the formula and solve for your unknown. All right, in a styrene calorimeter, 1 gram of sulfur, which is S8, was burned in oxygen to produce sulfur dioxide. Using the data given, find the molar heat of reaction for sulfur and add to the balanced equation. All right, so with this, they're asking us to find the molar enthalpy of reaction, or since we know that sulfur was burned, that word burned is the key word to tell you it's a combustion reaction, so that's why I'm putting C for sulfur. So that's what we're looking for. Now, looking at the data given, we're given the mass of water and the initial and final temperature of water. So I'm going to use these two to figure out my change in temperature. So again, remember that's going to be final minus initial. So 43.6 degrees Celsius minus 21.5 degrees Celsius. So that's going to give me 22.1 degrees Celsius. So this represents how much heat was gained by the water in this calorimeter. All right, so we are going to follow a similar format to what we did in the first example. So we already figured out the change in temperature of the water. Okay, and we're going to need to know how many moles of the substance that underwent the reaction in this. So in this case, since sulfur was burned in oxygen, sulfur is what's undergoing the chemical reaction. Okay, so sulfur burning is going to be the potential energy side of our formula. So we're going to find moles of sulfur. Okay, so moles is equal to mass divided by molar mass. So remember, sulfur is a polyatomic element, so whenever it's by itself, there's 8 of them. So that's going to help you figure out molar mass. So 1 gram divided by, now the molar mass of sulfur is 256.56 grams per mole. You can go to your periodic table to figure that out. So if we take 1 divided by 256.56, that's going to give us 0.00389, goes on forever. All right, so now we're going back to the heat lost is equal to heat gained. So we have the negative potential energy is equal to EK. So the potential energy is negative just because it's an exothermic reaction. How we know it's an exothermic reaction is because combustion reactions are exothermic. Okay, so I'm just going to flesh this out. So moles times the molar enthalpy of combustion of sulfur. So this time around, anything that's pink is or belongs to sulfur. And then MC delta T, so this all belongs to water. Anything that's blue belongs to water. Okay, we were asked to find the molar enthalpy. So we need to isolate for this, and we're doing the exact same thing. We're just dividing by negative moles. Okay. So our mass of water is 100 grams. Specific heat capacity of water is 4.19 joules per gram degree Celsius. The change in temperature was 22.1 degrees Celsius. And our moles was this value over here. So 0.003897 goes on forever. So I'm going to do the same thing. 100 times 4.19 times by 22.1, close the bracket, divide by negative answer, and that's what we get. So our units are joules per mole because grams cancels out, degrees Celsius cancels out, but joules and moles don't. All right, so let's look at our question here. Okay, so looks like the least amount of significant digits that we're given is 3. So my answer needs to be in 3 sig digs. So 1, 2, 3, there's my cutoff line. Gonna have to move the decimal 1, 2, 3, 4, 5, 6 spots to the left. So the molar enthalpy of combustion of sulfur is equal to negative 2.38 times 10 to the power of 6 joules per mole. Okay, so this is the molar enthalpy of combustion only for sulfur. All right. The question also says to add it to the balanced equation. So remember, when you are writing your thermochemical equations, you need to give it in terms of change in enthalpy, not change in molar enthalpy. Okay, so as a reminder here, change in enthalpy is found when you take moles and times by molar enthalpy. Okay, now since we have already taken into account the 1 gram of sulfur, now we need to take into account the moles of sulfur from the coefficient of the reaction. Okay, so this is just 1 mole of sulfur times by that negative 2.38 times 10 to the power of 6, which is still going to be negative 2.38 times 10 to the power of 6, but now we have it in joules, not just joules per mole. So just showing you what it looks like for units. The moles are canceling out. That's why we have it in joules now. Okay, if you're wondering if you could have this in kilojoules, yes, you absolutely could. Okay, so if you wanted to write this in kilojoules, it would be negative 2.38 times 10 to the power of 3 kilojoules. All right, so it does say to add this to the balanced chemical equation. Now, since this is a negative value, that means we need to put it on our product side, and I'm just going to arbitrarily choose to use our kilojoules value, but you could have also used the joules value. The reason why is because the question didn't specify what units to have. And there we have it. Okay, example 3. Predict the final temperature of an 850 gram copper bracelet that is initially at 21 degrees Celsius, so that's initial temperature, and is heated by burning 3.50 grams of propane in an open system, and they give us the molar enthalpy of combustion of propane as negative 2043.9 kilojoules per mole. Okay, so again, we're following the same starting point, where we're gonna figure out, we're gonna start with this heat lost is equal to heat gained. We need to have the moles of our substance undergoing a reaction. Okay, and we also need to expand the kinetic energy part of our formula to MC delta T. Okay, so since I know that I'm going to need to find moles, I'm going to put that over here. Okay, but I just wanted to talk about the formula for a little bit. So we know that it's a combustion reaction because propane is being burnt. So we have our negative EP is equal to EK. If we expand this, we have our moles times by our molar enthalpy of combustion for propane is equal to, now in this case, our kinetic energy terms, since there's no water here, our kinetic energy terms are going to be tied to copper instead of water because there's no water present. And copper is what's having, or is what's doing the temperature change. Okay? And since we're asked to find the final temperature, what I'm going to do first is we're first going to isolate for temperature change, and then we'll expand it later to kind of reveal the final temperature variable. Okay, so I'm going to divide by mass and specific heat. So anything that's blue belongs to copper here. So this is the formula that we're going to be using. Okay, so we have the molar enthalpy of combustion of propane. That's this. We have the mass of the copper bracelet. That's the 850. So we have that. We have specific heat of copper. We can look that up. We're looking for final temperature. We do already have initial temperature. So this is like this part is good enough for now. And all we need to do in order to get moving on this calculation is we need to find moles of propane. So we've got 3.50 grams of propane. So remember propane, that is on page 5 of your data booklet. And that's C3H8. So then the molar mass of it is going to be 44.11 grams per mole. All right, so now we can plug in our values. And you know what? Right now, I'm going to expand delta T into final minus initial. So mass was 850 grams, and then specific heat capacity of copper is 0.385. So that's joules per gram degrees Celsius. Okay, now the problem here is that our specific heat capacity is in joules, whereas our molar enthalpy is in kilojoules. Okay, so one way that you can get around this without doing too much extra work is if you add kilojoules, since the kilojoules, or since the kilo prefix is on the top and the bottom, ultimately that's not going to change this value. Okay, keep in mind the prefix that you add in the top and the bottom here has to be the same in order for this value to not change. All right, so now that kilojoules is dealt with, this creates a little bit more of a second problem as well. So now we have kilograms and grams. So our masses aren't in the same units. However, this is pretty easy to convert. Since there's 1,000 grams in a kilogram, you just need to move the decimal over 3 spots to the left. So turn this into 0.850, and that is now in kilograms. All right, and there we go. So 495.5768. Number keeps on going on forever. So what happened to our units is moles canceled out, kilograms canceled out, and kilojoules canceled out. So we're left with degrees Celsius. All right, now on the left-hand side, I'm going to take this 21 degrees Celsius and plug that in for my initial. And then we're just going to add it over. So our answer is going to be 516.5768 goes on forever, degrees Celsius. If we look at our question, it looks like the least amount of sig digs is 3. So my cutoff line will be right on the decimal. So my final temperature is going to be 517 degrees Celsius for the final temperature of the copper bracelet.